they deflected onto the wall. That simple. Now, because of course collimators aren't perfect, they should leave some amount of spread, as we outlined. And so, this spread should influence these atoms to go in all kinds of directions. Even if the collimator was perfect, surely these atoms all have different orientation. One could be this way, one could be that way, one could be this way. It wouldn't make sense if they all had the same orientation, right? And so the experiment was run by Gerlach, and it turned out they did not all have the same orientation. Good. What instead happened was, instead of a continuum like they expected, everything being hit, they didn't get one, but two unique orientations. There was one giant clump of them that went this way, and another giant clump of them that went that way. Why? That question was the catalyst behind quantum mechanics. Well, along with so many other things. This is overcomplicating it. But this question in specific is a very nice illustration of the strangeness of quantum mechanics. We know these things have to have been in all different kinds of orientations. So what happens such that you can't just say the collimator thing was too good because it didn't give just one orientation. It somehow gave two. There's something deeper going on here. And what is that deeper thing? Well, back then, scientists thought it was entirely classical. Maybe these atoms just happen to align with the same amount of angular momentum. Like maybe that's just what magnets and other kinds of things tend to do. That's just what happens, right? Magnets tell atoms they affect to just orient all in the same position, or maybe two different positions depending on which way they went, or I don't know which pole was closer to them. We can't tell. But it turned out that it was not classical. In fact, the classical model was completely wrong. In fact, the spin of these particles was not something that could just change on a whim or with a magnet. Spin, this sort of